Today we will understand and solve the minimum cost of climbing stairs. The problem sounds like this. On a staircase, the ith step has some non-negative cost of I assigned. Once you pay the cost, you can either climb 1 or 2 steps. You need to find a minimum cost to reach the top of the floor, and you can either start from the step with index 0 or the step with index 1. So what this problem wants to say is that, let's say we have this array called cost with 10, 15 and 20. We can either start with the step 0, or in this case step 1, 10, and we pay the cost 10, or we can directly go to 15, then we pay the cost 15. Then if we choose to go to step 1 and pay 10, then we can either go to 15 or to 20, and then from 20 we can go to the end. If we choose to go to 15, we can either go to 20 or we go to the end. From the title of the problem, we see that the request is to find the minimum cost, so we would choose to have a greedy approach to solving this problem, so we would always choose the minimum. If we look here at the second example that LeetCode gives, we can either go to step 1 and pay 1, or go to step 2 and pay 100. Of course, we choose to go to step 1 and so on. And also, this is a great problem as introduction to dynamic programming. A basic definition of dynamic programming is that you don't want to solve the same problem more than once. So you save the answer and apply that answer moving forward. So when you find yourself solving the same problem more than once, then you know you must think of a way to apply dynamic programming. Now that we have the problem clear in our heads, let's move forward to the tablet and draw the conceptual overview of the problem so that we can understand how to find the solution using a greedy approach and how to optimize it using dynamic programming. And after that, we will come back and code our solution. Welcome to the conceptual overview of the minimum cost of climbing stairs problem. As you can see here, as an example, I took this array containing 5, 15, 10, 25 and 20. I purposely didn't pick a sorted array so that you can see that the input doesn't have to be sorted. And I also drew the stairs here. This problem is a mix between a greedy algorithm problem and a dynamic programming, because we will use a greedy approach to solve it and we will use dynamic programming to optimize it. Now let's try to solve it conceptually and see how we would approach it in a greedy way. When I am at the start, I have two options: to either take one step or to take two steps. So I can either move to 5 or I can move to 15. Since we use a greedy approach, I will pick the minimum between the two because I want to find out the minimum cost. So I'm gonna be at 5. The second step follows the same approach. I have a choice to either go to 15 or to 10. So I can either go to 15 or I can go to 10. The minimum between 15 and 10 is 10. So I'm gonna step this time 2 steps and move to 10. Now from 10 I have once again two options to either go to 25 or to 20, and I choose to go to the minimum between the two, to 20. And from here on I'm at the end. So I solved the problem. Now if I sum up all the costs, I see that the result is 5, the cost of going to first step, plus 10 plus 20, the result is 35. So the minimum cost of climbing the stairs is 35. Now I'm gonna show you the tree of solving this problem so you can see how dynamic programming can help us solve it in an optimal way. So given our step 1, 2, 3, 4 and 5, I'm gonna conceptually put 0 as the start and conceptually put 6 at the end. So if I'm at the start at 0, I have two options: to either go to step 1 or to go to step 2. So I'm gonna draw these options: to 1 or to step 2. The cost to go to step 1 is 5. The cost to go to step 2 is 15. From step 1 I have again two options: to either go to step 2 or to step 3. The cost to go to step 2 from step 1 is 15. The cost to go to step 3 is 10. From 2 once again I have the option to go to step 3 or to step 4. 2 to 3 cost is 10. 2 to 4 cost is 25. Now from 3 I can either go to 4 or I can go to 5. 3 to 4 cost is 25. 3 to 5 is 20. Now from 5 I would go to the end. From 4 I can either go to 5 and then to the end. For 4 to 5 the cost is 20, or I can go directly to the end. Now if we compute the cost for all these steps, we see that if we choose the approach to always take one step, 1 2 3 4 5, it's 75. Then if I choose to skip from step 4 until the end, I have 20, 30, 55. So in this case the cost would be 55. If I choose from step 3 to skip to step 5 and then until the end, I have 20, 30 plus 20 again, 50. Now let's compute for step 4. Once again from step 4 I can either go to step 5 or until the end, and here of course I reach the end. From 4 to step 5 the cost is 20, and from 4 until the end it's 0 of course. So in this case I have 5 plus 15, 20, plus 25, 45, plus 20 equals 65. Or if I choose to skip the step 5, I have 5 plus 15, let me show you, 5 plus 15, 20, plus 25, 45. So here the cost would be 45. Now we're at step 3. Let's compute the 3 solution for step 3. At 3 I have the option to go once again to 4 or to 5, and then again from 4 I can either go to either the end or to 5. I put the end here because I don't have any more room, and from 5 I go to the end, 3 to 5 and then the end. And then from 2, if I start computing again, I can see that I can either go to 3 or to 4. Then again from 3 I can go to 4, 5. From 4 I can either go to 5 or till the end. So just as you can see here, this problem from 2 to 4 to the end, we solved it already. We solved it here. 2 to 3 to 5, we solved it again here. So we see that also 5 until the end, we solved it so many times. So we see that we solved the same problem many times. We already have those results, so we don't need to always compute them. So here is where dynamic programming comes to help, because what we can do is to use memoization and save those results of those intermediate problems so that we don't have to compute them every time. So when we need to compute them, we can just retrieve them. Now there are two ways to solve this problem dynamically. We can either modify our cost array, or we can use two variables, because as you can see at each step we only need the last two results to compute the final one. So at each step we are only interested in the previous two steps, so we only need to memorize or to save the last two results. So how do we do that? So if I were to write this in some kind of pseudocode, I would create a last step and the second to last step, second to last, and I would keep my previous two results in these two variables. So now, because I have the last two, so if I would have to loop through the array, I would go for 2 until the end, and I would say what? I would say that current, I'll have to keep a current sum. Current is the cost of I, so the current step where I am, plus the minimum between the last two steps, because to apply dynamic programming we do a bottom up, so bottom up optimization, meaning that at each step, like I said before, we keep in mind only the result of the previous two last steps. So if we use a bottom-up approach, here at the end I know already what is the cost at 5, at 5 I know already what is the cost at 3, and so on. So I only need these last two variables. So I have the minimum between the last and the second to last, and then of course the second to last becomes last, and the last one becomes current, and this is it basically. And at the end I would just return the minimum between the last and the second to last. So once again, I hope everything is quite clear how we chose to apply dynamic programming to optimize this problem. As you can see, of course, here once we reach the end, then we choose the minimum between the last two steps, and then that is our correct result. In terms of time and space complexity, since we go through the array only once, is O(n), and space complexity, we use constant space to save the second to last, the last, and the current variables, so then it's O(1). I hope that this conceptual overview made it more clear for you how we can use greedy and dynamic programming together. Now let's move to the code so that we can also have a visual understanding of the code, and maybe when you combine the drawing with the code, everything will be more clear. We will start with the Python implementation of our problem. So in this case, let's initialize n with being the length of the array, because we will use it a few times here. Then we handle the edge cases and we say if n equals 0, so we don't have any elements in the array, we just return 0. Also, if n equals 1, which means we have only one cost in our array, then we return cost of 0, because we would only have to pay the cost for that one stair. As we saw in the conceptual overview, we need to define two variables. I call them last, which will be cost of 1 to start with, because we know we have at least two elements, because we handled the edge cases here, so we know we have two elements in the array at least. So the last, I will call it cost of 1, and the second to last will be cost of 0. Now we are iterating through the array starting at step 2, so I'm gonna say for I in range 2 to n. As I said in the conceptual overview, current is cost of I, so cost of current step, plus the minimum between last and second to last. Now the second to last becomes last, and last will become current. And we have to return the minimum between the last and the second to last. I strongly suggest that you code it yourself as well, but also debug it, so go through each step. I didn't do it in the conceptual overview because it's pretty straightforward. It was much more important there to understand how to reach the solution actually, and also optimize it, rather than going through each step, because it's pretty simple. It's just a for loop, but you can do it yourself so that you can understand it even better. So now let's run the code. Yeah, as we can see, passed, so let's submit it, and it's accepted. Now let's move on to the Java code and see how we would implement our solution in Java. Let's also code our solution in Java. We'll declare n as being the cost.length, the length of the cost array, because I'm going to use it frequently, and I'm going to say if n equals 0 to handle the edge cases, then return 0, and the other edge case is if n, and I'm going to show you in a moment why this is an edge case. If n equals 1, then return cost of 0. Is pretty obvious. If you have only one stair, just return the cost of that stair. Now, as we saw in the conceptual overview, I'm gonna define two variables, last, which is cost of 1, and we know for sure we have at least two elements in the array because we handled this edge case where n equals 1. That's why that one is an edge case. So int last is cost of 1. Now second to last will be cost of 0. And now we're gonna loop through the array from starting at position 2. I'm gonna define current, which will take the cost of the current step plus the minimum between the last and the second to last. Let's not name this variable like in Python, let's name it like in Java. So this will be second also. Nice, good. Now second to last becomes last, and last becomes current. And the solution is to return the minimum between the last and second to last. As I mentioned also when I coded the Python solution, I suggest that you also go to through each step and debug this problem, so you see how the algorithm goes. It's pretty straightforward and pretty easy, but it's better for you to understand better this algorithm. I didn't do it in the conceptual overview because, as I said before, but I'll repeat myself because maybe you skipped through the Python implementation. I didn't do it in the conceptual overview because it's pretty simple and you can do it yourself. I prefer there to show you how we found the solution using the greedy approach and how we optimize it using dynamic programming. Good, let's test our solution. Yeah, and as we can see, it's a really good solution. It's faster than 100% and uses less memory than 92%. I really hope that what I explained was clear enough, and if not, please leave your suggestions in the comments below. Also, if this helped you understand better the minimum cost of climbing stairs problem, please give this video a like as it helps with the YouTube algorithm. Also, please subscribe and click the bell button to receive notifications as I release new videos every week. Thank you for watching and see you in the next one.